Thanks. All right, let's go ahead and get started. Today, we're going to actually start getting to application of what this all means. First thing we're going to talk about are processes, which are really the basis of any type of work that is done on your machine. So a process actually represents a program that is running, but it not only represents the program, it represents everything that's with that program for the operating system in order to schedule it. Because remember, we talked earlier, you have multitasking operating systems, so you have to figure out how can you run multiple processes on the same machine, especially since you may not have a processor for every program that's running, but you want to at least give the illusion that all of them are running simultaneously. So we're going to talk about how do modern operating systems handle processes, what they need to store about it, how do they switch from one process to another, and how do they decide when to switch from one to another. All right, so let's see. Concept, state, scheduling, talked about that a little, operations, inter-process communication, and then some examples of other IPC. And client-server systems as well, although that's not too applicable right now. All right, process, program, and everything associated with that program needed to run it. All right, great. Okay, operating system can actually execute these in different ways. First is a batch system. Has anyone used a batch system before? You. Oh, how'd that go?
Oh, that was nice.
It was nice?
Yeah, no, it was nice. I mean, I did this using punch cards.
Okay, so way back then.
So this is actually, but I've also used the batch system without that as well. But so you have your job, everything is done. You can turn your job in with everybody else, and they process it as a batch.
Mm-hmm.
So of course, you're on their schedule, not your schedule.
Yep.
And your priority is not their priority.
Right.
And that's it's like, here I am. Oh, I worked really hard at this. This is really great. It's like, okay, come back Tuesday. It's like, that's.
Yeah, so this was batch system. Probably can guess from the description. Doesn't happen anymore. Well, probably does not happen anymore. I know how the military works. It's probably used somewhere. But the idea is that everyone would submit their program, punch cards, maybe submit it. Well, I don't even know if we could do it electronically anymore, but they would submit it somehow, and then they would line up all those programs in one giant batch, and they would send it through the machine, and then it would give an output for each program, and then you come back days later, and hopefully your program executed correctly. Hopefully you can all see that for today, that is a terrible solution. So instead we have something called time sharing system, or time shared systems, where we're going to share the time on a system by switching in and out of different programs. So instead of running one after another, we'll run part of this one, then jump to part of the next one, then run to part of the next one.
Another problem with batch systems and jobs and such is that, okay, so you were actually working, you weren't working several parts of one program, you were working several programs during a time period.
Mm-hmm.
And you turn your stuff in, you'd have stuff in different phases, fluxes.
Yep.
And so you'd have to switch your mindset from one, okay, what am I doing on this program now? Okay, what am I doing on this one?
Yeah, there's a lot of problems with a long delay coming back from your program, especially when you're trying to debug it, which is just not acceptable, especially nowadays since we have computers that have fixed this issue. Okay, textbook uses the word job and process almost interchangeably, so keep that in mind. Job and process are essentially the same thing. Let's see, process is a program, and execution must progress in a sequential fashion. Your program's still going to execute sequentially, one line after another. All right, what does it keep track of? First is your program counter. Hopefully you remember that from architecture. You have program counter telling where that program is currently executing. The stack, part of the memory. You got to keep track of where you are in function calls, as well as any memory associated with your function calls. The data section, aka the heap, extra memory as well, and then there's going to be a lot of bookkeeping information that the operating system stores as well. So it's not just a program anymore, it's a bunch of different things. Actually, what's not listed here is your text section, which is the actual program itself. That needs to be loaded. The next bullet point's the fun one. A process can start another process. And of course, if that means a process can start another process, then the process it started can start another one, so forth and so on. And then, of course, there's some deletion of processes, so it can kind of go up and down a lot, deciding what's actually running and not. The operating system's job is to intelligently switch between processes. Do you think there is well, actually, let me rephrase that. Is there a theoretical optimal switching pattern given processes and a machine?
Yes.
How close do you think the operating system is to that?
Miles.
Right. Keep that in mind. This is not the OS cannot foresee what's coming down the pipe, so it cannot always schedule things perfectly. So you have to come up with heuristics about how to schedule it. So don't think this is something.
26 westbound yesterday.
Right. That operating system, same thing. How did it know this process was going to happen? Was going to just die in the middle of it, right?
And also too, the theoretical optimums are based upon goals.
Yes.
Because they're not, so there's not one for, this will work great for everything.
It's based on a goal, which may actually change during the execution of a program.
Process, you're like, oh, wait, that is.
Right. Right. So it pretty much can't be solved. So the OS just has to make it as good a guess as possible. All right. Big caveat here. Job and process are interchangeable. Process and thread are not. They are two different things. They are related, but they are not the same thing. And hopefully we'll get into that. Actually, we're probably not going to get into that today. So a thread is basically, think of it as a process minus a bunch of bookkeeping and other information. It's a mini process, so to speak. But we'll get to that later in class. Process and memory. Hopefully this looks familiar from architecture. Your text is your program. Your data is part of data is actually your global memory, and then also usually it contains the heap as well. Notice they're connected. The heap grows towards the other direction. In this example, we have it growing up, and the stack grows down. And what happens when they meet?
Bad stuff.
Bad stuff. What happens if they meet and you ask for more memory?
Depends on which one asked. Depends on which one asked, because the heap could overwrite the stack, and the stack could overwrite the heap.
Well, in a modern operating system, what would actually happen?
Oh, the counters would look at you.
Same fault.
Yeah, you get a seg fault, you get an error.
Yeah, we get an error.
Right, in an old operating system, it would just start writing over each other, and
Now it knows
we're cool.
where the pointer is. It knows, that both pointers equal 0, you're done.
There's if you remember from architecture, it actually has that virtual memory.
Mm-hmm.
Yeah, it will actually keep track of where it should be and where it shouldn't be. So it'll tell you when you've gone over the heap or the stack. All right, a process can be in different states. This is part of the bookkeeping. So it can be new, aka the process has been created, but it hasn't started running yet. It's running, meaning that instructions are currently being executed on this process. It is waiting. The process is waiting for some event to occur. Typically I/O, it's waiting for the user to type something on the keyboard. Ready means that the process is waiting to be assigned in the processor. What's the difference between running and ready?
Running is after ready.
Yeah.
Sure, okay, you can go from ready to running because it's waiting to execute on a processor, then it's running. And then let's say it hasn't completed, but the OS says, all right, it's someone else's turn. It's basically what it's saying. What state do you think it'd go back to?
Waiting.
Actually, it'd go back to
because
ready.
It doesn't need anything else.
It
It's
doesn't
already
need
ready,
anything.
yeah.
The OS just says, all right, you've had enough. It's someone else's turn. Now, if all of a sudden it's up running and it says, hey, look, we need to, it says, I need something from the keyboard, then the OS says, all right, you're waiting for this I/O event to complete. And then terminated means that it has finished execution and the OS needs to clean this guy up. Here's a nice little graph for you. So it's new, the OS is cool with it, it'll go into the ready state. So ready comes after new, because it has to actually allocate this process and get it ready. Then when it says, all right, you're on the CPU, it's back into running. And then from running, it actually can have two different things. It's either interrupted by the OS saying, hey, look, someone else's turn, in which case it goes back to ready. Or running says, okay, I need to wait for an I/O event, and then it goes back to waiting. Now notice that once the I/O event completes, it doesn't go back to running, it actually goes back to ready, because the OS, okay, you've cleared, you're no longer waiting because I actually have the information for you. So I'm going to put you back on the queue, the job scheduler. And then when you execute, you can go back to executing and be done with it. All right, and in this graph, you can only go from terminated from running. In all actuality, there are situations where at any point you can be terminated via the kill command. You can always kill a process, in which case, no matter where it is in this, it just goes over to terminated. All right, any questions? Because that's a good comment. It's important to understand why and when these are happening. All good? All right, we're doing great. Some more information about each process. I'm not going to guarantee this is all of it, but this is a good portion for this class. The process state, well, that's not very descriptive. We'll skip that.
Running waiting thing?
Huh?
Running waiting.
Running waiting? Okay, that thing, yeah. So when it says process state, I'm like, well, that's all this information, but you mean the state of the process. That's all right. Program counter, that's just hopefully a 32-bit or 64-bit register. CPU register values and usage. Ooh, how many of those are there? Depends. Good answer. Depends on your architecture. If this was old x86, it'd be 4. Newer ones have 16. Other versions like Spark and PowerPC will have 32, and MIPS 32. And then if you're running, I think it's Itanium, there's 128 of them. But you need to know the values of each register and what they're currently used for, because sometimes you need to keep track of, okay, what's the kernel pointer, what's the program counter, etc. Though really the program counter is usually part of the register, but we separate them out for what we're doing. CPU scheduling information. Is it waiting? I mean, why? This is just extra information. Basically, how long has it been on the queue? Maybe might be a good piece of information. Is it really waiting for? Has it been waiting a long time to get the I/O? Is actually a really important piece of information, because the scheduler in general, if someone's waiting for I/O, once it receives the I/O, it wants to run that process as fast as possible, because chances are it's been waiting a very long time for it, so it wants to give it a higher priority. All right, memory management information. Where in memory is it storing? Also, if it's sharing memory, that needs to be stored there as well. Counting information, what's the process ID, what's some other characteristics, and then the I/O status. Which devices has it been connected to? Which files has it opened? Et cetera, which are actually connected to this process. So a process control block. Hopefully you can see there's a lot here. It's not just a simple program executing. Oh, here's a common way of doing it. Process state, process number, PID, process counter, all the registers, maybe some memory list of open files, and further information as well. That's the control block. Where the program is currently residing in memory, any data, or maybe where the heap is for it as well. Okay, CPU switch. Here we go. You got process 0 and process 1. Hopefully this is clear in your mind. It should be, yeah, this should make some sense. We're trying to execute process 0, and all of a sudden it's being interrupted by a system call. It would save its state, reload from PCB1, aka it's loading process 1. Then it can start executing process 1. Then knows that it has process 1 has interrupt system call, save the state of PCB1, load in PCB0, and then it can go back to actually executing process 0. So notice what's happening from this picture. This process 0 has been executing, it's been interrupted, so process 1 can execute, then process 1 will be interrupted, so then process 0 can execute it as well.
It's a lot of idle time.
Yeah, from this picture, it looks like there is a lot of idle time, and that is a problem when scheduling multiple processes, is that there is a cost, actually a significant cost, from doing a context switch from one process to another. So you want to minimize this while still giving the illusion of programs running simultaneously. Hopefully you can see how those two things are at odds with each other. Any questions? All right. All right, so the job queue or the process queue, set of all processes in the system. So that's the master queue of everything. You also would have a secondary queue of what processes are ready. Yeah, they're in main memory, they're ready, and they're waiting to be executed. Okay, these guys are ready to execute. Let's go and do it. Device queues, set of processes waiting on an I/O device. Now notice we call them queues. Almost always these are a type of priority queue in order to figure out which process needs to execute next. And if one jumps in, maybe it can get ahead of some other ones because it's important to run this guy.
So not FIFO.
It is first in, first out, like a regular queue, but since it's a priority, it may be first in, then jump a couple of things, and then first out. It's still like a queue, just not pure FIFO, like you're trying to tell me. I'm trying to make sure you understood I agree with you. Sorry. Queues only contain a pointer or a process ID, not the entire process. Hopefully that makes sense, because that's going to be a lot faster than trying to copy a whole program state or process each time. And yeah, they can be a fixed size array or linked list, depending on which is best. If they're a fixed size array, it's usually a heap because it's a priority queue. All right, cool. So we can have different versions here. So you have the ready queue, the head, this is the linked list version. It has two processes, 7 and 2 in the ready. Magnetic tape is empty, probably will be empty for a long time. I don't think we have too many of those running around anymore. The disk. All right, so this is interesting. Why do we have a ready queue and a disk queue? It's going to be on the disk. This might be a little hard to remember. I just breezed over it.
Because the transfer rate from the disk.
Right. So what's going on here is, remember, the ready queue are processes that are currently residing in memory. So they are in memory, they are ready to go. The disk is going to actually have some processes that haven't been loaded into memory yet. So this is to signify, hey, look, we're going to have to load these into memory. Why would that be a good idea to separate these two?
You don't want to try to run processes straight from your disk.
Right. So the idea is that if it's a disk process, it needs to be loaded into main memory. And since a disk takes a very long time to read data, maybe you could start reading one of these, and while it's reading, go back up to your ready queue and start executing a process. Then when you get interrupted, throw that guy to the back of the queue, come back and read the disk, finish reading that disk into memory. So it's kind of a way to save some time. And then you have terminal unit. That's if you're using a terminal, aka serial connection.
Why are head and tail pointing to the same?
Because that linked list has an element of 1, in which case the head and the tail are the same. All right. Whew, this is kind of a confusing one. So you get the ready queue, runs the CPU, and then if all of a sudden it has an I/O request, it goes to the I/O queue for I/O that can eventually go back to the ready queue. Time slice expired. Ooh, that's the first time we've seen the word time slice. A lot of times in operating systems, you'll be given a time slice, aka how much time you are allowed to use on the CPU before you're going to be interrupted. Most CPUs have a timer on them, such that the kernel can basically set the timer, and then once that timer executes, it interrupts the process, sends an interrupt to the processor, and then starts executing the kernel from there. Of course, if your time slice expired, then you just go back to the ready queue. It's someone else's turn. All right, you can fork a child, then the child can execute. Child executes, and this actually should be 2 lines because you have the child going onto the ready queue as well as yourself going onto the ready queue. Forking means that you take your current process and you make a copy of it. And that's just the basic tool in order to create multiple processes.
But when you go to fork, the parent goes back to the ready queue, but the child continues on executing in the CPU.
It depends on the scheduler. If I were to write a scheduler, the way I would do it is once you call fork, it copies the process into memory, creates a the PCB for it and then throws both into the ready queue, is the way I would do it. The operating system, of course, can have multiple choices on how it does it, but if I were to do it, that's how I would accomplish it. And then waiting for interrupt, you're in the I/O queue. That's, well, waiting for an interrupt is something besides I/O. Maybe you're waiting and a signal from another process or something along those lines, something internal. All right. Before we go on, I think it's a good time that we actually start coding, because we haven't seen any code yet in this class, and that always makes me sad, so we need to start. Right, Matt? Code always makes you happy, Matt. Yes, it does. So I've created a class code directory for this course. It has not been uploaded to GitHub. Remind me at the end of this class to commit everything we write today up to GitHub so that you can actually see what we've done. You can go ahead and create a fork directory. And then I'll go and I'll just make a fork.c. So we'll go ahead and include, we'll do std io.h, int main, int argc, char star argv, return 0. And let me make sure I can compile that. And yeah, it does nothing. Okay, great. So we're going to open back up fork. I'm actually going to create a new terminal. So notice up here I have two tabs. One tab over here, another tab over here. They're both terminals. I can switch between the two. I'll just do gcc fork.c, and we'll go ahead and run it right afterwards. All right, it does great. Okay, so I told you there's a command called fork. Fork is actually one of the most basic system calls out there. It's usually one of the first system calls that an operating system has to attend to, because it's the basic way to create new processes. Well, let's go ahead and look at, whoa, that's not what I meant to type. Let's go ahead and do a man on fork. Create a child process. So we have to include uni std.h. All right, let's go ahead and do that. And then fork. So it creates a new process by duplicating the calling process. The new one's referred to as child. The calling process is referred to as the parent. So a parent is going to create a child. Your current process will create a child and therefore become a parent of a child process. They both run in separate memory spaces. At the time fork, both memory spaces have the same content. But afterwards, memory writes from the child is only going to occur to its memory space, and anything the parent writes to will only occur to its memory space. So they're going to have a copy of whatever occurred when you call the forked function. Child process is exact duplicate of the parent except for the following points. The child has its own process ID, does not match the ID of any existing processing group. Don't worry about processing groups, but just knows that it has its own PID. And then the child's parent process ID is the same as the parent's process ID. There are tools to use to get your parent's ID. The child does not inherit its parent's memory locks, so any type of locking is not there. Okay, there's actually going to be a lot of this. Basically, there's a couple things it doesn't inherit specifically to just that make sense a lot of times with locks and certain I/O. But in general, the child is going to inherit most everything. All right. So if I go over here, and we'll just do a printf hello. If I were to skip back here and run, did I not save? Fork.c, printf hello, return 0. Oh. Probably should output it correctly. All right, hello. Perfect. If I were to fork it first, what should be the output of this program? When I compile and run, what's going to happen?
Oh, you should just get some sort of numerical value back.
I'm going to call fork, and what does that do?
Creates
Possibly
a
an unending stream of processes that
Okay.
will print hello.
Right, so how many processes are going to hit hello?
Unlimited.
No, fork only forks once. So you had one process. When you hit fork, you're going to have two processes.
Which is gonna call fork.
No. After this function is called, you have two processes executing. It's not going to start over at main. It's going to start execution right after the call to fork.
Oh, so the fork will print hello, and then the parent will print hello.
Close. They will both print hello. There is no guarantee to the order.
So whichever gets the queue.
Yeah, you got it.
If it was in a loop instead, would it keep forking them? Or?
Right, and that is called a fork bomb. No, that was a common way to, DDoS a system back in the day. Have a program that called fork over and over again, call fork. So it kept creating processes that called fork, and everyone just kept forking until, the system blew up. Right, so fork, remember that. And this makes sense because when you fork, you're copying the process. Well, the process has the same program counter as the old one, so of course it's going to go to the next function call or the next line of code because it has the same program counter. It's not going to start from the beginning again. So this should print hello twice, and it does. All right, now what happens?
3 times.
No, 4 times.
4 times.
Okay, both of them.
Because they're both going to fork. All right. So let's go head back. Now, a couple other things so you can get PID. Oh, we have to include sys/type, so let me go ahead and do that. PID returns the process ID of the calling process. This often is used by routines that generate unique temporary file names. Well, you just want to get the process ID of the calling, so you just call get PID. All right. So we'll go up here and go PID _ type my PID, and then after fork we'll have my PID equals get PID. I'll have hello, and I'll just do %D, and that should be okay. My PID. Actually, it's probably %LD now that I think about it, because I'm on a 64-bit machine. So yeah, I'm 1519, 1527. All right. Every time you run it, you're probably going to get 2 different IDs. It's not guaranteed that they are sequential. Although since you're calling fork pretty quickly, they probably will be, but that does not have to be the case. The numbers could be completely apart. The parent, actually, which one's the parent and which one's the child?
You still don't know.
You still don't know.
26.
You still don't know. It's not guaranteed because the child's number could be before it. Because you're not guaranteed in ordering. So we actually don't know yet. So how are we going to know which one's the parent and which one's the child?
Hello, I'm parent so-and-so. Hello, I'm child so-and-so.
Get the PID first, call it parent PID.
Okay.
Before the fork, and then get the PID after the fork.
Perfect. But let me, we skipped over something real quick. Fork returns a PID. What is that return value? Let's see.
That's the parents.
On success, the PID of the child process is returned in the parent and 0 is returned in the child. So, jumping back over here. Yeah, a little confusing.
Parent PID.
I'll go return PID. So we'll say return PID equals fork. So if return PID equals 0, what does that mean? Print F, I'm the child. All right. And then else, printf. Oh wow, typing. I'm the parent. There we go.
Still gonna.
Okay. Now, is it guaranteed? Here's another good question. That the hello I'm 1550 is the parent?
No.
No. Again, that is not guaranteed. Chances are it is in this situation because it executed very quickly, but the operating system could have easily interrupted it. In fact, let's go ahead and force that just for, oh, that's not what I wanted. man 3. Sleep. You just call sleep. Okay, cool. And it's even thread safe. Oop, I don't know why I got rid of it. So I'm going to call sleep real quick. No, the child happened first that time. Hey, look, the child's still happening first.
You're calling sleep before you print anything.
Oh yeah, that's terrible, Paul. Yep. It could happen either way.
But you're still not sure which was which.
No, you're still not sure. Probably the
You
best.
take out the new line.
No. Well, that may do it. A better way. My PID. There, get the PID afterwards, and then just make the printf, associate what your PID is on the print. So now when you do that, we'll get rid of this sleep real quick. Now you know 1624 is the parent. So anything that starts with 1624, you know is a parent, and now the child is that one over there. All right. Probably very helpful when you are debugging a program, aka a lab, that's going to be assigned in this class today. Just throwing that out there. Okay.
Never use this again. Got it.
Depends on what you're going to do. Yeah, if you're going to web development, probably not. If you're going to become any type of device driver or system level, yeah, you'll be doing this. You'll be doing this. But it's good to understand what's going on in the background, that's for sure. All right, now, I actually forgot how you get your parent ID. Let's see if we can figure that out real quick. Oh, returns the process ID of the parent. Hey, you get the PID. That sounds great. What does that return? Let's see, conforming to description. Hey, there's no return. I guess we're going to have to play with it.
Try and manage the PID.
Yeah, we're going to do this.
Or just play.
My parent is, and then we'll do %LD. Notice I am still keeping up here the print of what my PID is. That way I know for sure that it's this child, this person that's talking it, and not someone else. I'm going to do it here. And I'm going to delete, I'm going to comment out this line for now. My parent is, so I'm the child, my parent is 1. So my parent is 1422, and then here is my parent is 1. Well, that's interesting.
Man, get PPID.
That's what I did. Man, get. Returns the process ID of the parent of the calling process. Well, that shouldn't have happened. These functions are always successful. That's cute. Why do I not believe that? Wow. Kill, temp, credentials, PID names. Huh. Wonder why we got back a 1. That's interesting.
Was the parent returning?
I think you're supposed to pass in.
Ah, you know what? You are correct. What happened? Now this time it worked. What happened? Oh, that's great.
I don't know why it worked.
No, this is great. This is a great example because this is just tells you how terribly subtle multi-process programming is. What happened? Why is the first one?
Ended before the child process.
You got it. So the parent ended. So of course its parent is now 1 because it lost its parent and now it got shoved up to probably the init parent. So now that's what its process is. ID. Basically the parent, the way the OS Linux will do it is it'll try and give you a new parent. But if it's 1, chances are your parent died. Don't cry too much.
So if you're calling it from the parent process, it's calling the.
Well, notice my process is 1422. Notice the process right here, now parent process is always 1422.
Is that OS though? Or?
That's probably bash.
Okay.
Yeah, let's go ps-aux grep 1422.
That's what I.
Bash,
thought.
boom. So it is, bash is what's running, which is what fork called fork, because when you execute a command, it is calling fork to run your process. And then that was the immediate parent.
What was 1422?
So notice in both of these executions, I have I'm a parent, and my parent of 1650 is 1422.
Oh, got you.
In both of these. Well, that means 1422 has been running. Well, probably has been running. Not guaranteed, but probably has been running the whole time. And I looked up, all right, let's do a ps-aux, aka give me all the processes and give me an extended explanation of each one of it. grep for 1422. Looks like bash is running. Notice 1677, what's that representing here?
You're correct.
Yep, is the grep itself. Because that is another process. All this making sense? Are there a lot of processes running?
Oh, yeah.
Oh yeah, there's a lot of processes running. I think this is going to be good for now. Figure out how to create a child. You figure out how to look for your parent.
When you're all in one line on your program, printf, from printf.
There's one more command we need to do. But go ahead. What was your question?
Well, when you put it all in one line, what's that percentage LD?
Long D, which is decimal, aka
okay.
Not decimal. I'm sorry. Long integer is what it is. I forget why D stands for an int, but it does. No, it's not a double. It's an integer. A double would be a %LF because it's a long floating point. And D, I always forget what the D stood for. And you have to do LD because it's a long integer, which is just a long, aka 64-bit, because I'm on a 64-bit machine. All right. Last thing, very important. If you are the parent, it is usually important to make sure that your children die off first before you do. So there's a program called wait. You have to install, or you have to include syswait. So let's go over here and do that. And now what happens? You type in wait, pass in nothing. Actually, I think it wants you to pass in null, doesn't it? W status, we don't care about the status. Good. AK 0. And then we'll put a printf. Okay, children are done. I won't be so morbid. Now when you go over here and you run it, the parent will the child will always be able to get its parent ID because the parent is waiting for its children to complete before it ends. This is a very good common practice. You want the parent process to be alive for the entire execution of its children. Hence the wait command. Over here. All right. Any questions about this code?
When you put wait above. That's it. So if you got a number back, or no, if you got a 0, then it's a child.
Right. Let me go ahead.
Okay.
So this creates a child
Right.
process, gets my PID if I'm a child. Of course, there's only one child, and this is if I'm a parent.
If you're the parent, you
Wait
want to
for
go wait.
all children to complete. Now it's going to wait for all children to complete, and that includes the children's grandchildren, so forth and so on. And then we're done.
So parents store their children?
Yeah, parents keep track of their children.
So could you create a list of all the children?
Yeah, as long as you are doing it, as long as you keep forking, you can keep track of all your children, yes.
Oh, but you can't keep track of your grandchildren.
You can, but that's going to require more work.
Oh.
Well, it's got to inherently keep track of them, though, if it can wait for them.
Right, the operating system's doing that. Any other questions? This is good.
So if you were doing a loop, as you said, you wanted to do several children's and children's children, children's children, and you wanted to go back and, like, let's say you wanted then, okay, I've just completed my last child. Well, I want that one to complete before the next one completes, before the next one completes.
Right. If you're doing it correctly, your children are going to wait for their grandchildren to complete before they complete, so then the parent can wait for the regular children to complete for it to complete.
So you could have a wait null in your loop if you were doing a loop for
The children, right. There's a, I don't know if it's wait null, I will have to look it up, but you would want to have some type of wait on the children's children. Yeah, you know what I'm trying to say.
Yeah, wait null would mean the whole process. No, you wouldn't want.
Well, remember,
The parent.
the parent and the child are completely separate processes. They
Oh,
just happen to
okay.
be linked because the operating system is keeping track of the fact that the child is a copy of the parent.
Okay.
It only takes one parent to create a child on an operating system.
And they don't share memory.
They do not share memory, but they have a copy of each other's memory when they were forked or created.
So if you have a variable before the fork, it'll have that.
So that's a good point. Let's do that. And what do you want to call this? My age equals, we'll do 35. And then down here, if I'm a child, well, I'll say my age equals 14. And then we'll go down here and I'll just have my age is, and we'll do %D, putting in my age. And down here, wait for the children to complete, and then I'll print off my age and then say children are done. So what's going to happen is you're going to fork, the child is going to set his age to 14, print everything out, the parent's going to say I'm the parent in my PID, it's going to wait for the child to complete. So after wait, the child would have executed my age equals 14. And then it's going to print off my age here. From everything I said, what should the parent's age be? 35, and the child's age would be 14.
Why? Okay, so you've got my PID. Why? Well, okay, on the third print. F.
Down here?
Yes.
Right here?
Yep.
Mm-hmm.
You've got my PID, and then you changed. What's my age? Is the actual? You're printing out the
This variable up
14,
here.
The variable. You know the my age equals 14 variable.
Right, correct.
Okay, and the my PID. What is that? We're using that. That's the.
That's to just make sure you know who I am,
Okay, gotcha.
in case some things start getting mixed up, which they will once you start writing complex programs. So there you go. I'm the child, my parent is 1713, my age is 14, then 1713. Notice that's why I did this, and so you know that 1713, which is the parent, I'm the parent up here, my age is 35. So you know the parent is saying his value is 35 and the parent and the child is 14. Notice when I run this again, just iterate, the PIDs have changed. Of course, parent of the parent hasn't because I haven't closed bash yet. Any good questions? Any questions, actually?
No. Oh, never mind. No.
Let me put up the code again. Any other questions about this code? I think this is pretty good basic understanding of fork. All right. Let me go ahead and pause or go ahead.
I know. We'll get the.
Let me pause.